Okay, so we want to talk a little bit about what happens when a material is heated, or cooled for that matter. So there's going to be a temperature change. Most materials, I think most people understand, will contract when cooled and expand when heated. As we see here, if we apply heat to the axial bar shown, it will elongate a delta, and we give it a subscript t to denote that it's a change in length or a displacement as a result of the temperature change. To understand this, we need to look at the coefficient of thermal expansion. The coefficient of thermal expansion is a material property which will describe how a material will behave due to temperature change. The change in unit length or strain of a material that is caused by a change in temperature of 1 degree Celsius is called the coefficient of thermal expansion and is denoted by the term alpha. Here we see then, if we were to interpret that into equations, the strain is equal to alpha, or the coefficient of thermal expansion, multiplied by delta T, the temperature change. Because strain is change per unit length, then if we multiply it by the length, we will actually get the displacement, and we write down the equation displacement is equal to alpha delta T L. For there to be thermal stresses, we need to have a statically indeterminate or a fully constrained problem. Okay, so if a member is restrained during a temperature change, thermal stresses are induced. It wants to get larger in this case due to an increase in temperature, but unfortunately it can't because the end conditions are holding it in place. In order to calculate what this stress is resulting from the temperature change, we go through a multi-step process. The first thing we do, similar to how we solve the other statically indeterminate axial bar, is we remove the restraint, make it redundant if you will, and calculate what expansion would have occurred had it been unrestrained. So we apply our equation delta T equals alpha delta TL, and we calculate the displacement due to temperature change. We then calculate the force that would be necessary to return this member to its original size or to cause a displacement P in the opposite direction. So delta T must be equal to delta P, or negative delta P for that matter. We do have an equation already for delta P equals PL over EA, which we can combine with the equation delta T equals alpha delta TL, put them together, and we can determine that the load due to the temperature change is AE alpha delta T, or if we divide through by area, the stress or the thermal stress is equal to alpha delta T E.